Hi everyone and welcome to my YouTube channel. It's been a long time since my last video, but hopefully right now I have much more time to continue with the lessons. Like right now we'll be continuing our inequalities playlist. Let's do a quick recap of what inequalities we have discussed so far. So we started the playlist by discussing the AMGM, the arithmetic mean, geometric mean inequality, which was basically the most important inequality, and it's really like a basic inequality that you're going to need like in nearly all like both, whether you're solving a simple inequality or an advanced inequality as well. Then we discussed kind of a hack for the AMGM, which was a Muirhead. Muirhead, as we saw, it's just a kind of a special version of the AMGM, but it makes your life way easier when you have symmetric inequalities. Then we discussed Cauchy's inequality, and of course Tito's lemma as well. Cauchy was like as important as the AMGM. It has many applications, and of course Tito is just a version of it, Tito's lemma. Then we moved to discuss Holder, and Holder, of course, it was just like let's say a generalization of Cauchy, as we saw in the lessons we discussed earlier. After that, after we discussed the classical inequalities, we then started discussing some techniques, some algebraic techniques and manipulations that you can do to help you simplify inequalities and deal with some, let's say, weird conditions that you have in the question. We started, for example, with the Ravi transformation to handle like let's say side lengths of a triangle, Ravi transformation. Then we saw like other techniques like substitutions to get rid of conditions, like in the ABC equals 1 substitution. And we saw like also the normalization lesson in which we did the opposite. We had a homogenized inequality and we turned it into a non-homogeneous inequality, but now we have some nice conditions. Okay, and in today's video we'll be starting with the rearrangements inequality, which is also a classical inequality. It's not as classical as the like the AMGM and Cauchy, not as important, but it definitely has some like very good applications. And in fact, some of the recent IMO problems like have been actually, let's say, you need to use at some point the rearrangement inequality. So it's definitely worth it. All right, so I hope you guys are excited. So what are we waiting for? Let's get started. All right, so let's start by discussing the rearrangement inequality itself. What's the general statement of it? Instead of immediately reading the statement, I prefer to work with some, let's say, examples to make it more understandable. So what is it exactly? Let's take something like we're going to need two sequences basically. Let's say this is the first, and let's actually, for the sake of simplicity, take it like the same sequence again. Now, our goal here is actually to take kind of a combination of these two sequences. So this is our first sequence, let's call it like the A sequence, and this is the B sequence. So our goal is to take something like this, for example. You can take 10 with 5, 5 maybe with 1, and 1 with 10. And then, if you do this, you're going to get, for example, the sum, or let's say S is equal to 10 times 5 plus 5 times 1 plus 1 times 10. So this is like the sum that you get here. You can, of course, evaluate it. 50 plus 5 plus 10. And you get the answer is 65. Okay. So, of course, as you can see, you have many actually ways to do that. Like you can maybe take this. You can maybe take something like this. You have like many possibilities. What we're interested here, actually, we're interested in, can we know the order of those? Like, can we know which one is greater, which one is smaller? Well, actually, it turns out that you cannot really know their order, without evaluating them. However, what you can definitely know is which one is the maximal sum, how to get the maximal S, and how to get the minimal S. So basically this is the rearrangement inequality. It just tells you how to get the maximal sum and how to get the minimal sum. So right now I really want you to think about it yourself. How do you get the maximal sum out of those combinations? So I want you to try to take some combinations and see yourself which one is the greatest. Well, I hope you get it right, but basically you can easily see that the greatest sum, the maximal S that you can get, is simple. You're just going to get this 10 with the 10, and the 5 with the 5, and the 1 with the 1. The reason is kind of straightforward here. When you take 10 with 10, you get 100, right? It's very big. Compared to, for example, if you take 10 with 1, it's going to be 10, very small. Or 10 with 5, 50. Not even compared with when you multiply big stuff together. Although like the smaller stuff, when you apply them together, they're really small, but it's at least better than taking the small with the big, because then the big is like two, let's say, it's not really like doing its job like well. So right now, of course, that means the maximal sum, like S max, is basically 10 times 10 plus 5 times 5 plus 1 times 1. So what you can see here is like if you have two sequences, by the way, they are not necessarily the same. I can just like, let's say, make this 100, 50, and 10 maybe, and just do the same exact thing. You can still see that the greatest thing will be taking this 10 with the 100. So it seems that generally speaking, if you want to get the maximal S, the maximal sum, then you should take the greatest number with the greatest number, and the second greatest with the second greatest, and so on. So this is how you get the S max, like the X max, the maximal S. Now the question is how to get the minimal S. How to get the minimal S? Well, just like we followed this logic, you can easily see that to get the minimal, you're going to take the maximal, but you don't want it to grow to participate in a good way. So you want it to be participating in the worst way possible. So you're going to pair it with the smallest thing, and here of course the same thing, and this with this. So it seems the idea here is that we do exactly the reverse here. If you want to get the S min, the minimal S, then you're just going to get the maximal with the minimal, and the second maximal with the second minimal, and so on. Of course, you can evaluate those and see that yourself. Okay, so right now we hopefully you understand what exactly is the rearrangement. What does it mean, and that it really makes sense logically. So right now let's read the general statement. Let's say we have two sequences. Of course, they are real numbers, by the way. They can even be negative, no problem. Keep that in mind. Rearrangement, you can apply it even when they are negative. AMGM, you cannot apply it with negative, especially when you you want to take roots, of course, or like even for example with odd stuff. So keep that in mind. Anyway, here we have the first sequence, and of course we need to order them in descending order here, and we also have another sequence. We also order them. As you can see here, I just made them distinct. You will see why I did that in a second. Right now, our goal is to get those kinds of permutations, right? Let's say we're going to keep the B's as themselves, and we just want to take the A's with them. So that we're going just to get, generally speaking, something like this. This is like, I kept here B1, B2, and so on till Bn. I'm just playing with the A. So I just took some permutation, of A primes, of A1, the sequence A1, A2 till AN. And this is like what I get generally. So the idea is, what's the maximal one? The maximal one is this. The maximal one is if you pair stuff like this. The maximal with the maximal, the minimal with the minimal, and so on. This is the maximal S. And the minimal S will going to be, of course, as we said, like this, and so on till like this. So as you can see here, we take exactly the exact reverse. We pair the greatest with the smallest. I mean the opposite, the smallest with the greatest, and so on. Okay, so this is exactly the rearrangement, actually. I'm sorry, here, this one. Okay, now the question is, when does the equality hold? When does the equality hold? Okay, first of all, let's actually prove the rearrangement. Generally speaking, we saw that it really makes sense, but it's always a good idea to prove like inequalities, even like if you, especially when you're discussing it for the first time or studying it. Okay, so let's see. Generally speaking, let's say that we have like the b as the, like we said, something like this, then bn, and of course we have the same thing for the AIs. Well, actually, right now we have like just the other sequence, which is AA. Now, if you have something random like this, and you want to maximize it, it seems that if you have, let's say, two numbers that are not arranged properly. So, for example, maybe you have those. We don't care about b1 and b2, as we said, we already arranged those. But let's say the a1 prime and a2 prime, they are swapped. So a1 prime is less than a2 prime. We're going to show that, in fact, if you reverse that, you're going to get a bigger value. Of course, if we can do that, then we can apply it for any two, like let's say any two numbers that are arranged in a bad way. We're going to keep fixing, and at the end of the day, of course, we'll just get the arranged like sequence. So that's basically our method of proof here. So let's just look at something like this. Let's say we have here AI and BI, AJ, BJ, prime, prime. And let's assume here, of course, that they are in a bad way. So remember, the B's are already like in descending order. So we already know that BI is greater than BJ. Of course, here I'm assuming that I is greater than J. However, the thing we have here is that those guys are swapped. So we have the opposite. Our goal is to show, if you want to make them like even greater, then you should do the opposite. So that means you should do this. Okay. So let's see, how can we prove this? Well, clearly when you have something like this, you should try to group stuff together and may hopefully factorize. So if you just took those to the LHS, left-hand side, and then factorized, you're going to have this, and you can take BI minus BJ as a common factor. I mean like AJ actually, as a common factor, then BI minus BJ. Do the same, take this here, and take AI prime, common factor. Now it's, let's make it actually negative, and still BI minus BJ. And hence, we just need to show this is greater than 0. Now we can take this as a common factor. So it's just at the end of the day, this times BI minus BJ greater than 0. Well, let's see. This thing here, we know BI greater than BJ, so it's positive. This thing here, we know that AJ prime is greater than AI prime, so it's positive as well. So indeed, this is true. And indeed, this is true. So now what you can do, you can keep applying this process each time. Like each time you have two that are not arranged properly, just flip them. If you keep doing that, of course, at the end of the day, you will get it like in this sequence. Okay. And now the idea is when the equality holds. Well, guess what? Here, if the equality holds, then when we're doing those flips, then like everything is the same, right? So those guys here should be like 0 when you're doing that. So if you want like to flip those, then that means either this is 0 or this is 0. So either those two are equal or those two are equal. That's of course if you're flipping them here. Well, the idea is what I did here. We said that the B's are distinct. If the B's are distinct, then that means the AIs actually are equal, right? They are equal from here. So that means AI prime equals AJ prime, which means that if you're doing them So everything you're flipping here should be basically the same. Like if you flip this and you want them to be at the end of the day equal to the greatest sum, then they should be equal. So it's a little confusing, but if you look here, for example, and you want this to be this, the equality to hold, then that means some of them, of course, you're not flipping when they are the same. Let's say like an is the same as an prime, an minus 1 is the same as an minus 1 prime, and so on. But the stuff that you actually flip, like let's say for example those were bad, you flip them, they should be equal. So if they are equal, and at the end of the day they're going to be the same as this, right, as these, because you're going to keep flipping until you make it the same as this. So what you can actually say after all of that, kind of not really like elegant discussion, you can see that the equality holds only if the first sequence, this random sequence, is the same as the sequence that does the job for us, the greatest sequence, like this one. Of course, this only works for actually distinct b's. If the b's were not distinct, this is going to be some trouble for us, because, for example, take the simplest example, when all the b's are equal. If all the b's are equal, then look at this thing here and look at this thing here. It doesn't really matter, right? They are always equal. You can take the b as a common factor if they are all equal, and then just going to be b times sigma a, and here b times sigma a. So yeah, the rearrangement equality case is a little not very elegant. However, most of the times actually when you apply it, you're going really just to need to show that it's greater than or equal to. And if you know that those guys are distinct, one of the sequences is like distinct, then you know that the other one should have the same like this, something like this. And of course we also have the other part of the rearrangement, which is this, to get the least thing. Again, you can repeat the same discussion to get the smallest one. Keep repeating the same algorithm, and also the equality holds when you have the same arrangement this way. Okay, so I hope now you understand exactly what's the rearrangement, and you have a sense of where exactly did it come from. Now let's go ahead and start working with some simple examples. Okay, so now we need to prove this simple inequality. Sigma a squared is greater than or equal to sigma ab, or ABC are just some real numbers. Okay, as you know, of course, this is just the simplest inequality in the world for AMGM, but our goal here is just to try to prove it using the rearrangement inequality. So how can we do that? Well, if you look here, of course, to apply rearrangement, you need to have two sequences. So what exactly are the two sequences here that are going to produce this and this for us? Well, clearly the easiest one is that will come to your mind is like this sequence and the same sequence actually again, right? At the end of the day, to get the LHS, you're just going to like take them like this, right? And you got the LHS. To get the RHS, you're just going to get like AB, BC, and CA. Okay, so now it's time to apply rearrangement. Well, guess what? You cannot apply rearrangement unless you know the order of the sequences, right? But here, like, they didn't really tell us the order. So that means we need to discuss all possible cases, right? If they arrange, like the order is A, B, C, or C, A, B, or B, C, A, and so on. You have 3 factorial permutations, right? So 6 cases. Well, actually, it turns out that no, that's not the case. You don't need really to do that. The idea is, if you look here, this thing is symmetric, right? This thing is symmetric. This thing is symmetric. So whenever you have symmetric quantities, symmetric stuff, then you can actually assume the order yourself without loss of generality. Because if you do it in like one of the orders, then you can actually do it in the others as well. So here you can easily just start your solution by saying assume without loss of generality A is greater than or equal to B, greater than or equal to C. Now if you take just these two sequences, let's see what is the maximal sum possible. The maximal sum possible is just to take them this way, right? So the maximal sum is this, and this thing is just some random sum that appears from here. We don't care whether it's the minimal or anything else, but we know that this thing is the maximal. So actually you're done. That's it. So you simply just say, like, by rearrangement, this thing is the maximal sum, and that means it's greater than the RHS, and you're done. That's it, simply. Alright, our second example is the following. Here we're given positive reals ABC, and we need to show that sigma A cube is greater than or equal to sigma A square B. Okay, so again, to apply rearrangement, as we said, you need to define your sequences, right? So what are our sequences here? How can we get those? Well, again, you should look at ABC, and in order to get some stuff like this, then clearly here you can have like the sigma, like the ABC, but you have also A square, right? B square, C square. So just define the other one as A square, B square, C square. Now clearly the LHS you're going to get it by taking this, and the right one you can get it like with this: A square B, B square C, and C square A. Okay, that's like done. Now like condition 2, you need to have an ordered sequence, right? So here our inequality is symmetric, right? So we can assume without loss of generality that A is greater than B greater than C, and that just means that those guys here are ordered, right? Like they're ordered, A, B, C, and A square, B square, C square, they have the same orientation here. So that just means that this thing is the greatest sum, and this is just some random sum. So the LHS indeed is greater than the RHS, and you're done, right? Well, no. If you thought that's the case, then you have been fooled. Be careful. This is actually a very important thing, because if you look here, we said that the whole thing is symmetric. Well, this thing is symmetric, for sure, but is this symmetric? No, this is not symmetric. This is cyclic, remember? When we said like the sigma cyclic, and when we define the sigma symmetric, sigma, if this thing should be symmetric, then if you have A square B, then you should also have AB squared, right? Do you have AB squared here? Well, you don't. So that means this thing here is not symmetric. So you cannot just assume without loss of generality that A greater than B greater than C. No. This thing is cyclic. So that means what can you do? You need to discuss the three factorial permutations. Well, there is one thing actually you can say, which is when you have a cyclic thing, remember cyclic is just like this. They are just moving like in this kind of triangle or circle, let's say. So you can actually assume the max, which one is the max or which one is the min. So you can, for example, say that A is the max. So if A is the max, then you either have B is greater than C or C greater than B. So that means you just have to discuss two cases. Now if you discuss the two cases, for example, if we discuss B greater than C, then you're going to have the same here. Now if C is greater than B, then you can, guess what, just do this. And again, like they are handled in the same way. Well, it seems that they're like you're really doing the same thing, right? Isn't there really a way to do this without discussing cases? Well, actually, yes, there is. The idea is the left-hand side is symmetric. The right-hand side is not. We don't care about this. The idea is if you look at this sequence here and this sequence here, those have the same orientation, regardless of whether A greater than B greater than C. Those always have the same orientation, these two sequences. So if A, then C, then B, then A square, then C square, then B square. That's their order. Or if we have C greater than B greater than A, then C square is greater than B square greater than A square. So that means the two sequences have the same orientation. If they have the same order, or let's say orientation or whatever, then what's the greatest sum possible? Guess what? It's just that like to get the same orientation, right? Because if they have the same order, then you're just going to take the maximal with the maximal, minimal with minimal, and so on. So that means even if you don't know the order actually, you can still apply the rearrangement, here, even if you don't know the order. But you just need to know that these two sequences have the same orientation. So like let's say A1 is the kth, then B1 is also the kth one, and so on. So keeping that in mind, that means here we can immediately do the problem by just saying that these two have the same orientation, same order. So that just means that the maximal sum possible is indeed this thing here, and this thing is just some random one. So we're done, that's it. No discussing of any cases. Alright, so that's it. Alright, our third example is the following. So here we're given ABC greater than or equal to 0, and we need to just to show sigma A cube is greater than 3ABC. Again, if you can see, this is easily by AMGM derived. In fact, our goal is to prove then the AMGM itself. So we want to get the AMGM using the rearrangement. This is like really a nice thing to keep in mind. You're linking big inequalities together. Okay. Anyway, how can we prove this with the rearrangement? Again, to apply rearrangement, you need to have some sequences, right? So let's see, how can we get this sequence and this sequence? Clearly, this sequence is just ABC plus ABC plus ABC. Here you have A cube, B cube, C cube. How exactly can you get those? Can you get those actually from two sequences? Well, what can you say? Like ABC, for example. And how exactly can you get this one here? If you think about it, it's impossible to get those from two sequences, both this and this. So, in fact, what you need actually is three sequences. If you have three sequences, then the LHS is like this, this, and this. The RHS is like this. Then, wait, I guess this B, C, and A, and then C, A, and B. Exactly. However, the question is, can you really apply the rearrangement on three sequences? Well, guess what? You can only apply the rearrangement on the three sequences only for the S max, the maximal sum. Because think about it, still it makes sense. If you want to have the greatest sum possible, then you should get the greatest numbers together, group them together, and then the second greatest together, and so on till the smallest numbers together, right? It makes sense, just like in the same way we did it for the two sequences. So yes, actually it is true. However, you need to be careful. Here, the sequences need to be positive. So if you want to generalize the rearrangement on actually not just three sequences, but in, let's say, n sequences, then you're going to have the numbers to be positive. So keep that in mind. If you're working with two sequences, not necessarily. Anyway, using that, keeping that in mind, again we can do the same idea we did before. Either you can say here it's like symmetric, both are symmetric, so you can assume A greater than B greater than C, or you can just look at again the same thing that we said before, which is this thing alone is enough for us. Like those all have the same orientation, so in order to get the maximal sum, you just get the greatest together and so on. So that means this thing is the greatest sum, and this thing is some random one. So yeah, we're done. That's it. It's correct. Yeah. So we're done with that. Now, how exactly can we generalize to get AMGM? Before actually we generalize to get AMGM, one thing, the generalization we talked about only is true for S max. But what about S min, like the minimal value, the minimal S? Think about it. Can you here get what is the minimal S? Before, when you had two sequences, we took the max with the min, right? The max with the min and so on, something like that. Well, here what can you say? Okay, this is the max, get it with the min, but then what? Shall we take the min or the max? So as you can see, that doesn't makes no sense. So actually, you cannot apply the generalization for the smallest s, only for the s max, let's say. Okay, right now let's go ahead and establish the AMGM. Well, what's the AMGM? The AMGM, you just have a bunch of positive numbers, and then like non-negative numbers, and then you have AI to the n greater than or equal to basically pi ai's, right? Okay, let's actually write it. A1, A2, A3, so on till AN. I'm going to write those as well. A1 to the N, A2 to the N, and so on till AN to the N. And here, of course, you have N as well, because it's the N was here, then we just move it here. Okay, so how can you show this with the AMG, with the rearrangement? Think about it. Well, we need to have some sequences. Of course, the simplest is just to take this, and we can take it actually how many times? N times, right? Now, those are positive. To get the maximal, those all have the same orientation. To get the maximal sum possible, we just take them like this, like this. This establishes the LHS. To get this is the maximal sum. To get the RHS, you can clearly get those guys N times. For example, one diagonally, and then you can do it like this and do it like this and so on. Okay, so yeah, that's it. We have established the AMGM. Guess what? From the rearrangements inequality, that shows you the importance and the really the AMGM is really a powerful inequality, since it establishes one of the most powerful inequalities, and that is the AMGM. Our last example for today is the following. As you know, no inequality lesson is complete unless you can show Nesbitt's inequality using it. Remember Nesbitt's inequality? We have shown this inequality in the Muirhead by simply expanding everything and applying Muirhead. We also showed it using Tito's inequality, or you can say Cauchy, whatever. And now we're just actually doing it again for this lesson, rearrangement as well. Okay, so let's see how exactly can we do that. First of all, you need to have some sequences, right? Let's have a look at the LHS. Okay, you have A here, you have B plus C here. Well, to get sequence, you want to have something like this, right? XY. Well, probably the only way you can think about it is X to be A and Y to be 1 over B plus C, right? That's it, to make sense. Okay, so of course right now you can see that this thing here is symmetric, right? It's symmetric. Clearly this thing is symmetric, so hopefully you can assume that A greater than B greater than C without loss of generality. Now our sequences A, B, C, and 1 over B plus C, 1 over C plus A, 1 over A plus B. You can see that if this is in this way, the descending order. Is this in descending order? Let's see. 1 over B plus C. Right now, when you have stuff like these, like fractions, then if you want this to be very large, then you have a very small denominator, right? And indeed, how to get the smallest denominator? By pairing B with C, right? The smallest stuff. And then come C plus A. Basically what you can say actually to get this, you can do it step by step if you want. You can say that B plus C is less than C plus A less than A plus B. Clearly this is true. C is less than B, and here B is less than A. So this thing is true. Then you can just flip it, flip it, take the reciprocal like this, and flip everything, flip the inequalities, and now you're good. So always you can get this and then get this. So now indeed we know that they have the same order. So that means that it's indeed the greatest sum. That's the S max. Okay, however, how can we get a 3 over 2? Well, you cannot get 3 over 2, of course, because you can only get other sequences, right? So let's actually try to apply some other sequences. So for example, the S max, that is the LHS, is actually greater than, for example, let's take some random one. Now let's take maybe this with this, this with this, and this with this. So A, you can say it's sigma A over A plus C, right? Okay. One other possibility, of course, this this alone is not enough, because you cannot say that this is just greater than 3 over 2. Another possibility you can do, we can also get LHS is greater than, and now what we can do, for example, here we got, of course, sigma A over A plus C. So perhaps you can take also sigma c over a plus c. But how do we get this? Let's see. C, a plus c. Then we go for like next a with this and b with this, right? Now you can easily see that you got just sigma c over a plus c. Okay, so that means from rearrangement we got this and this, but none of those alone is going to give you what you want, 3 over 2, 3 over 2. However, what we can do is, if you look at these two, if you add them, those are going to add to 1, right? Exactly. So that means if we add the 2, you're going to get 2 of the LHS is greater than or equal to 1 plus 1 plus 1, that's 3. So indeed, that just means that LHS is greater than 3 over 2. And guess what? That's exactly what we want. And we're done. We have shown Nesbitt's inequality, and which finished the question. Alright, so as a quick recap, today we learned the rearrangements inequality. What's the statement? Basically, we saw that whenever you have two sequences and they are ordered in the same order, then the maximal sum will be if they have the same orientation, then they just take them in the same order that you have. And to have the s the minimal s, you just do it in the reverse. So you need actually to have the reverse. You just reverse the first one and take it with the other one. We saw, of course, the equality when the equality holds, but remember that for the equality to hold, you need the b sequence to be distinct. Okay, then we saw just some simple applications, like here the very standard one. Whenever you have a symmetric inequality, you can assume without loss of generality that a is greater than b greater than c, and just apply the rearrangement here directly. Here we are careful because this thing is not symmetric. We cannot assume without loss of generality that a b greater than b greater than c. This is the most common mistake students do when they are learning the rearrangement. Instead, here what we said is that these two sequences, they have the same orientation, and hence the S max is simply if you get them in the same order. So this thing is the maximal S, and hence it's greater than this, whatever it is. And by the way, just one thing, you need to be careful. You need to always show that you can get both by this sequence. Sometimes it might be a little tricky, but you can be fooled sometimes that you think that your sequence work. However, you cannot get the RHS from this sequences. So make sure to always check that yes, you can. Then we of course generalize the rearrangement to any n sequence actually. We can always find the S max if they have the same orientation. But they need to be positive, be careful. And here of course we did it for 3, and we actually generalized to get A and GM generally speaking. Finally, we ended our lesson with the Nesbitt's inequality, and we saw that sometimes it's not really a direct rearrangement. Of course, you need to combine some stuff. So here we just took the first sequence and the other sequence. The other sequence can sometimes be complicated, like here it's fractions as you saw. But you can do it step by step to show that they have the same arrangement, like this. So that means that this thing is the maximal S. Now you can apply some inequalities. You cannot really get it immediately, but you can, for example, get this, or you can get this. But if you combine them together, now you get the inequality that you want. And hence we're done. Alright, so we discussed the rearrangement, but not fully. In the next lesson, we'll be solving a couple of IMO problems, one old IMO problem and one recent IMO problem. Let me know what do you think the IMO problems we're going to discuss are. I hope you guys liked the video. If you do, please share it with your friends, and see you guys in the next video.